Yes or no? Expectation of S of n into R n minus k is nothing but the correlation function correspond to S and R with k as the, because they are bicentenary, just subtract this from this and you get only this difference between the two times, which the one time is n minus k, other time is n, so difference between them is equal to k. What about the second term? Minus HGs are constants, j is equal to 0 to n minus 1, L minus 1. And then the expectations on this and this, R and R, and same random variables, except the time instants are different, and these are also bicentenary. So, the correlation function will be RSS, difference between one and the other, which is j minus k or k minus. And this should be equal to 0 for all k.
Shouldn't it be R?
What is that? I am sorry. This is the problem. Okay? So, if I solve this set of equations, because this is known, so I get a set of simultaneous equations in Hj. If I solve those L number set of equations, and then I get the coefficient corresponding to Hj, and that give me the coefficients here that specify this filter, optimum filter. So, if you now expand this, RR0, RR1, RR2, up to RRL minus 1. It goes on like this. We are writing a matrix. I am writing this n number of equations in matrix manner, nothing different from that. So, I need to find this vector. You can find out by taking inverse of this and multiplying by that. This is known, this is known. So, you take an inverse of this and find out what is the values of H0. But if you observe this matrix here, there is something beautiful property of this matrix. Here is R0, RR0, here also RR0. So, the whole diagonal will have the same value, similarly this diagonal, similarly this diagonal, and so on and so forth. Such a matrix which has this property of along any diagonal, principal diagonal, the values are all same, has a name for it, called a, what is the name? Topology. And this equation which arose out of that equation, set of equations, are what are known as Joule-Walker equations. And more of the story is that these coefficients corresponding to the impulse response of the filter will depend upon the correlation functions of the signal with the observation and the observation itself, right. We have agreed Rn is equal to Sn plus Nn. So, what is RSS? What are we looking for? Or SRK and RRK. Then what is appearing in this? Some k values corresponding to 1, 2, 3, 4, so on. What is this equal to? Nothing but expected value of Sk into Sk plus Nk. R is nothing but Rk is nothing but this. Okay, I should not write that. Yes, J, some J, and this is J plus K. This is RS by definition. What is this equal to? If you look at this, there is Sj into Sj minus K expectation, and these are correlated definitely, and hence this will be equal to RSSK. What about the second one? The correlation between the signal and the noise, and the assumption is that the signal is an independent one compared to with respect to noise. So, obviously, this correlation, this expectation will be equal to 0. So, basically RSRK is nothing but RSS. So, I can also replace this by SS here with that assumption that the signal and noise are uncorrelated, which is the most situation. This is the scenario, except in very special cases there is a correlation between this and this. Most problems these are uncorrelated. Similarly, what is RRK? RRK will be, you substitute here same thing, expected value of Sj plus Nj into Sj minus K plus Nj minus K. This and this are correlated, this and this are not correlated, this and this are not correlated, this and this are correlated. So, this just becomes equal to RSSK plus RNNK. So, Rn and K is the correlation function of noise samples separated by a number equal to K. And this white noise, what happens? White noise samples. Only when K is equal to 0, it has a value. If K is not equal to 0, they are uncorrelated. So, this will be like, if it is white, it will be some sigma square into delta n, delta K. So, this in this point here, I can replace this by RSS 0 plus sigma square. All this will have that, whereas all this will not have any noise part of it, because RSS 1 that point is 0. So, this will be replaced by RSS 1. Okay, noise component is 0 because white noise. So, this matrix now changes to this kind of a matrix here, with only diagonal having a additional term here sigma n square, and this being the same as what you have here for RSS. So, you invert this matrix and find out what is the filter coefficients, and that is the optimum linear filter, which is optimum for the Gaussian situation. And the filter is given by this with those values obtained from there. This Yule-Walker equation turned out to be equations came up much later from the continuous version of the same problem, where RT, observation as a function of time, contains a signal t plus n of t. Same problem, except continuous situation, where observation is RT and the signal is s of t plus nt. This nt and s, all these are Gaussian processes. And then if the observation is also Gaussian process, obviously. So, if this is a Gaussian process and then these are Gaussian processes and continuous observed over a period of time 0 to t, what is the optimum filter? That problem was solved by Wiener in somewhere 1942. And this set the ball rolling for optimum filters for extraction of signal from noise. And all the development took place in communication theory based on the work done by Wiener in World War II to shoot the planes. The whole idea is to shoot a plane. And we will extend this to Wiener filter in the next class, but this came later, since it looks simple, so I did this first, but in chronological order, this was done first and this came later.